I'm Darren. I've come all the way from Germany to talk today. I study at OTH Amberg-Weiden in Germany and also work there part-time. And my talk about side channel attacks and physical user input is part of what I did for my bachelor thesis. So what I want to go into is the first discovered side channel attack, because it's quite interesting, and the historical meaning and implications for this. Then I want to show you different side channel attacks on user input themselves, so what kind of medium you can use. And then I'm going to talk about the actual attack that I did, which used the acoustic side channel. So we'll talk about how I use the audio side channel, the segmentation of keystrokes, because you actually, if you want to look at which keystrokes might have been similar while typing, you do need to cut them out of the sample. Then clustering to find out which may be similar. Then passphrase recovery, because what I try to do is to get back passphrases, and then the actual results, so how well we did with this. So a side channel attack itself, it uses unintended effects to gather information, and it doesn't attack the algorithm or the process itself. So examples for this are like power consumption measurement, time differences. So for example, a very simple one of this is in a web server, user enumeration. If you give it like a username and it replies way faster, denying that this exists, whether you give it a password or not, then you know that this user might exist. So this is like a side channel that doesn't actually break the algorithm. It's just the time that you measure, or of course noises, which I will go into later. So the first side channel attack was from a now declassified NSA document, where an engineer at Bell Labs found a vulnerability in one of their typewriters. And you could see correlating spikes on an oscilloscope. And with an antenna and an amplifier, you could see this from almost 25 meters away. So you wouldn't have any trace on the device itself of this happening, the same as when I would record audio. You don't actually need to attack my laptop specifically. And the example was the Bell Labs 131B2 typewriter. I have a picture of a similar one here, which was used, and it's the same sort of mechanism. So this typewriter was used during the Second World War, and the German and Japanese forces were not able to break the algorithm because it used a one-time pad. But this shows that even though the one-time pad is theoretically safe, when you actually implement something, you still have these issues that present themselves, whereas you can then use a side channel to attack the actual device that implements this theoretically safe algorithm. So for actual side channel attacks on user input, one of the mediums you may use is acoustic inference. So this uses acoustic signals while someone is typing. And I've brought an example which is different from what I actually did. They use two microphones from a phone here, for example, to construct these parabolas. And this will give you, you can measure the time difference between the two microphones. And by that, you know, in which area of the keyboard it is. So you can see this color-coded here. So you kind of know which letter groups were hit. And then this enables you to brute force more smartly, or something like this. Another thing that you can do is use frequency analysis, which I've plotted here. So you would, for example, be able to see that the two middle samples look relatively simple, and you can use something like this to discern which keystrokes might have been the same. Another one you can use is movement-based inference. If people wear smartwatches, you can track the movement that was used during typing. So here they did this for a calculator, which could also be like a pin pad on your phone or whatever. And of course, regular typing. Here, of course, you see they have two hands. So most of you don't wear two smartwatches, I reckon. So you would actually pair this with acoustic or something else. Then you've got vibration-based inference, where they put a phone down on the same table as someone typing, and then you track the mechanical vibrations generated with this phone or some other device to, again, decipher what someone was typing. And then visual-based, this doesn't mean you have to look at the keyboard itself. It can also be more interesting, as they did here. So everyone probably knows the scenario. You're in a meeting and working while doing this. If you have your camera on, they tracked the angle of your shoulder to your actual upper arm. And because while you're typing, this moves, and they were able to then use this slight deviation while you're typing and your wrist is moving and all that to get back what you were typing. And then the last example that I have here is Wi-Fi channel state information. This is usually used to do error correction. And you can see that like while a Wi-Fi signal travels, it will interact with your body or other obstacles. And if you span a network like through a keyboard, you're able to have these deviations in the signal amplitude. And then, for example, if you look at the first word Apple, you can see that the two P's would look fairly similar. I mean, this is just an example, so it's perfect here. But in the real world, it would look similar enough, hopefully, to be able to get back to the original sample from that. Then for my actual attack, my audio side channel is either a placed microphone or the actual laptop microphone. So I had volunteers record themselves typing on a website. So the website would record what they should type and why they were typing. It would record it and then send it to my server. So I gathered the samples from there. So all the microphones were actual laptop microphones. So this could have been in a meeting or just a compromised device. Or of course, it's not that different from having some sort of microphone on the same table or something like that. So that is the assumption. And I did not want to use supervised learning. Does someone have an idea why this may be? So is anyone not familiar what supervised learning means? Okay, so pre-training models per user wouldn't really make practical sense here because you would have to have labeled samples of someone typing something. So installing a keylogger to then not use a keylogger in the practical world doesn't really make sense. So what we want to do is use it unsupervised, so we can use it on any target, any keyboard, and any environment. And for that, we will use clustering. And then after we have clustered, we'll use a dictionary attack to get back the actual words. So this is how the attack may look like. You have a microphone, you record the keystrokes, you segment them from the actual audio, then you compute some sort of features, I'll go into this, cluster based on these features, and then run the dictionary attack to get back actual words. So for segmentation and cutting out the keystrokes, we'll use adaptive thresholding. So you'll measure the loudness of a signal in a given time frame, and then cut out the louder parts of this, as you can see here. Of course, if you have a very loud environment, you may have to get more sophisticated than this, but for my example, this works. Then for the clustering, we can group the keys by sound then, or sound similarity. And possible features for this are MFCC, which is commonly used in AI applications for speech recognition. So it's some sort of feature that looks at frequency and so on, and filters out specific frequencies for speech, but it can also be used here and is often used in the literature as being a little bit better than, for example, the Fourier transform, which gives you the frequency in the actual sound bite. And then another feature we try out is cross-correlation, where you just cross-correlate every single keystroke with every other one to compute the similarity here. So to cluster, use k-means. Here's an example of this. So each of these colored cells would have a dot in the middle, which is the cluster assignment. And then all of these white dots would be my keystroke examples. These are, of course, quite a lot here to visualize this, but this is how it would look like. So I would have someone type, then compute the features of all the keystrokes, sort them in space, and then try to find out like distance-wise. So you can use Euclidean distance to group together keystrokes, and then hopefully these will be the same, which will then allow me to run a dictionary attack. So the assumptions here are the target language is known, which is English in my case here. Natural language text is used, and I did only use small letters and spaces to simply keep the size down of the experiment. And then the features of the clusters that we want to actually run a dictionary attack is the word length. And then we want the amount and positions of same characters in each word, because we don't actually know from a keystroke sound what letter exactly it might be, but we can still find out like natural language statistics. We can use these by looking at the letter frequencies themselves. So how this works is this is called a relationship encoding here. And what you do is you plot the word, or for example, the clusters then. So it could, instead of level, it could be 1, 2, 3, 2, 1, right? And then you would put a 1 wherever the same letter is, and a 0 wherever they differ. And then just to keep it simple and to make it easier to write, I use row major column order here to get like these string patterns that I wrote back there. So level or radar, which have completely different letters themselves, but they have the similar pattern, would be 001, 010, and then 3 zeros at the end. So this is how we can represent actual words without knowing what character they have. So here's an example for this, just to visualize this some more. The underscores is a cluster that I have guessed. So in natural language, the space bar, sorry about that, the space bar would be the delimiter. So this would be more often than other characters, depending on how large the message is. But if you don't get out a promising result, you can just use the next largest cluster and keep iterating from here. So now we know words. So 1, 2, 3, 4 might be a word. Then we have a space. Then 5, 1, 6, 6 might be a word. And then 7, 8, 9. And these are just the cluster assignments. And then we can use this to do this relationship encoding. So for the first word, which was acid here, you would have all zeros because they have no similar letters. And then this is just example words that you might find in a dictionary. So I use taco, myth, and acid for the first one, and so on. And then we can do a first step of filtering out candidates. So we would take the first word, get all our words that fit this relationship encoding from our dictionary, and then look if we can filter out some. So here we can see that we can't actually filter out any because all of them fit this, this pattern of not having any duplicated letters, right? So what we'll do, we'll simply concatenate the next. So we'll leave out the spacebar, concatenate the next word, forming a new word, and then we can do the same thing again. And I've tried to visualize this here. I've just realized with the actual monitor here, it's not that well to be seen. But for tackle doll, you have 2 O's and 2 L's, but they are in the wrong spot because for the actual word, you have the first letter and then the second letter of the second word being the same, whereas in tackle doll, the last letter of the first word would be the same as the second letter of the second word. So by forming these new words, we can slowly filter out from a whole dictionary which words we may be able to, which words may have been used. So in this example that I have formulated here, we only get 1 candidate, which is pretty nice. And then we can continue with the next 3 words for this to complete the passphrase. And then you can see here that acid jazz elk has to be correct because it has no common letters with the other 2 words previously, whereas acid jazz chi, for example, would have an I that is also an acid. So you can filter out this based on the positions of the actual letters and also which letters are the same. And then this is, of course, what we get. And here are the passwords that I generated to test out. So I had volunteers type these passwords. You don't, of course, need to memorize these. The passwords themselves are not as important. But we generated 5 passwords with a length 3 to 8, just to see how well we do. And then these are all the samples that I got from participants. So you can see not all participants typed out all samples, or not all samples were usable because of noise filtering issues and something like this. A lot of people had mechanical keyboards, but not all of them. And you will see later in the plot that I made where I am able to recover some passphrases. Most of them used mechanical keyboards that I was able to do this well for. So to get the actual model, I did a hyperparameter search. So this is, so the k-means algorithm depends on hyperparameters or the actual audio processing that I used. So we looked at the frequency analysis with Fourier transform or MFCC. And then also for cross-correlation, we use raw audio or FFT or MFCC here. And the cross-correlation, I've basically said this is another model, but it's just computing cross-correlation and then using k-means, whereas k-means would use these features directly. Then we did convolutional smoothing as an optional hyperparameter. We did scaling or normalizing of the audio, used a principal component analysis to potentially improve the results. And then the actual cutting out of the key strokes was also varied. So in the first section, you can see only the initial key press down is segmented, whereas in the second, the whole, so key press and up, which will also generate a sound, is segmented, just to see if this is better or worse. So here's the best models for each of them that we got. So for k-means, MFCC was the most promising, and for the cross-correlation, the raw audio. PCA was used for the k-means and not for the cross-correlation. Both of them did not use smoothing. Scaling was used by k-means, and cross-correlation did not use any scaling. And the keystrokes were actually segmented different. So for cross-correlation, we only segment the key press. And for keystroke span, in k-means, we segmented both the press and release to cluster. And then you can see cross-correlation was a little bit better. So the median score here is 93. So of course, if I get 100% correct cluster assignments, then the dictionary attack will be bang on. I can just run it and not worry about it. It will definitely find it. But as you can see, this is not perfect, and this is where the issues stem from, of course. An attacker may be able to run a hyperparameter tuning per participant or per target. So what you could imagine is, initially I get like a general model to use, then I cluster with this, and once I've recovered some sort of message, I run a hyperparameter search to improve this. And you can see that for some of these, we got like 100% there. So this might be very promising. But for the actual results here, I used the general model for all of the participants. So this is just one clustering and then using the dictionary attack to recover it. And it doesn't look too great. So what I figured I'd do is I just use 10 clusters, because that's the next logical step, right? And then we can see that previously we had 7 full passphrase recoveries here and a lot of partial recoveries. And going to 10 clusters, we can improve this to about, I think it was 17 full passphrase recoveries. And you can also see that 3 participants are way more colored in. So all the black boxes are samples that were unusable or not recorded. And then any fully colored rectangle is a full passphrase recovery here. And then you can see that the even the partial recoveries will improve here. So we could just keep doing this, right? But then at about 50 clusters, first of all, it gets increasingly difficult to run the attack because you need more compute. And then it kind of plateaus. So at 50 clusters, you don't really get more full passphrase recoveries. So what could we do from here? Let's just brute force was my idea. So now that I've actually recovered a few of the words, I'll just use combinations of them, of course. The issue with this is it kind of explodes computationally. So if you know about, so 2 to the power of 90 is about what like the most strong adversary might be able to compute. For some of the very long passphrases, we're at like 2 to the power of 104. So you wouldn't really want to compute this. For the 3 to 5 words, it may be computable this way. So what we can instead do, so this is like a naive kind of thing that someone might do. What we can, of course, do is take longer partial recoveries to go from. So this will bring down the computability of all of these to the realm of possibility, as you can see here. So all of these, if I'm not mistaken, should be computable because it's all like under 2 to the power of 50. So it would be like buying a coffee for the compute price. And then all the red rectangles are the full passphrase recoveries. I didn't mark in the partial recoveries here because it gets a bit crowded, and that's ultimately what we're interested in. But as you can see, 3 of the participants were actually fairly vulnerable to this, I would say, whereas the other ones weren't. And this is probably like typing style or the actual mechanical keyboard that was used that was attackable. So I want to, like some of you may have thought about this, instead of attacking only passphrases, you could of course attack emails, and this may be more promising because you can skip words and add them in later. So what I did here was I used an email from the Enron dataset. If anyone's not familiar, these are real actual emails that were published during an investigation. After that, they never did it again because you can read so much personal information from this. But yeah, I used this to run the algorithm itself. And then you can see all the green marked words, they were recovered. And then all the red ones were substituted in later. So you will construct a mapping of like a cluster to an actual natural language letter. And then you can substitute this in. And this email is basically readable here. So, and of course, once you have this mapping, you can then go back to the passphrases possibly and recover these. The reason I didn't do this is it was very difficult to get volunteers to type out 30 passphrases. If I had them type out like 300 words messages, I wouldn't have any volunteers. So, but as you can see, the attack can actually be used for emails and so on, and is, for this reason, still promising to recover actual messages. Here's the literature for all of the examples that I showed previously. If anyone has any questions, let me know. Oh yeah, and also if you want to read more about this, there's a paper being published soon. you can let me know, write me an email, Darren Fürst, OTH Amberg Weiden. You can Google me, I'm on the page, and you can shoot me an email. Or of course, chat to me after. Yeah, any questions? Yeah? Yeah. Yeah, I know. Well, as you've seen here, like you can, with passphrases, not so much, but you can kind of, and a passphrase would have to be typed correctly, so you get multiple attempts. But here, it kind of just corrects itself if you have a long enough message. And also, you don't need like the message doesn't have to be as long as if you use like bigram statistics or something like that, if you're familiar. So because you actually have the actual dictionary, the message can be way shorter just by nature of the algorithm that you use. But yeah, you just skip words and then add them later, as was done here. The only letter that wasn't really substituted correctly was desk. So the K was not there, but as a human, I can still read this. Yes?
How do you deal with like symbols? No, just put the
Yeah, well, I kind of cheated here, didn't I? So I only use small letters and space. Of course, in the real world, you have more letters, so you just have to iterate from there. Backspaces are, of course, a problem. But you could use the backspace as an actual symbol and then just go back. But of course, this makes like the amount of combinations explode as you get more into it. But again, with long enough messages, it's still kind of doable, I would reckon. No more questions? All right. Thank you.